Okay. Okay. Our third talk in this ocean history series is going to be given by John Gould, and it's got the title you can see there, From Swallow Floats to Argo. So, John, a few words about John. He joined what was then the National Institute of Oceanography, which is now NOC. He joined it in September 67, following a first degree at King's College in London and a master's in PhD from Bangor. He's worked on development of current meter data in the deep ocean about variability of currents from timescales from internal waves to weeks, months. And the focus has always been on ocean variability throughout his career. He's worked on many international projects. I won't list them all. The one I know him best from is the World Ocean Circulation Experiment. He's been on 34 ocean cruises, many as chief scientist. Has worked at Woods Hole, Scripps, CSIRO in Australia, and most latterly he directed large programs like WOS and Clive-R, and finally the Argo profiling float program that delivers now much of what we know about ocean temperature and salinity. And his main focus now in retirement is on documenting how ocean science has developed during his lifetime. So it's my great pleasure to introduce John. Off you go, John.
Well, thank you, Phil, and welcome everybody to, I think, the third of these history group seminars, which I hope you've been enjoying. So I'm going to take you on a story through over 50 years of the development of oceanography in the UK, and its theme is the development from swallow floats to the present Argo profiling float program. People who are new to oceanography today probably don't realize just what an enormous change has happened within the last half century, and certainly during the last 20 years or so. There are things that we can do now that could only be dreamt of 30 years ago. And for instance, here's some data that I collected from my laptop in my sitting room just a few days ago. Oh, where is it? I want to go back. Hang on. So if you want to know what the temperature and salinity are at 1,000 meters below the surface in some of the remotest parts of the ocean, you can do it. And you can do it thanks to an array of autonomous instruments that fill the world's deep ocean basins. This is almost, well, 20 years ago, this would have been regarded as the stuff of black magic, and now it's taken for granted. So how did we get to this situation? Where were the origins of this array? Who were the people involved? What were the steps involved in reaching this remarkable state of affairs? What I'm going to do is take you back to the mid-1950s. Before I started in oceanography, and certainly in an era where oceanographers would have quite happily, oceanographers on the Challenger expedition on a ship in the 1950s would have recognized the techniques and the equipment that were being used then. To give an idea of how ignorant we were of the state of the oceans, here is a table from a paper published in Deep Sea Research, which was the major journal in which oceanography was published in those days, by Ken Bowden. Ken Bowden at that time was working at the quite new National Institute of Oceanography. And the reason that he put this paper together on subsurface ocean current measurements was because there was a fundamental problem and challenge to oceanographers in those days. Uh, Thanks to Scandinavian oceanographers, we had developed what was known as the dynamic method of calculating the profile of currents in the deep ocean from measurements of temperature and salinity taken at quite widely separated stations. And just as one could calculate the strength of wind in the atmosphere from the atmospheric pressure field, so you could do this in the ocean from temperature and salinity measurements. They had, though, a fundamental problem in that they could only tell you about how the currents at one level related to the currents deeper down. There was no absolute reference as to what the currents in the deep ocean were. And this was the challenge of the day. And that was why Bowden wrote this paper to pull together all of the measurements that had been made. The fact that they could be put in one table says volumes about it. There were very few measurements. And how had they been made? By mechanical current meters like this one on the left, the Ekman current meter, which had a little propeller on the front, and it dropped little lead balls into a receptacle, and the distribution of the lead balls in various segments told you which way the currents had been flowing, and the number of lead balls in each one gave you the mean direction, and the number of turns of the rotor told you how fast the current was. Alternatively, you could hang a parachute or some other big drogue from a little buoy at the surface and measure where it drifted and assume that what was going on at the surface in this little buoy represented what was happening in the deep ocean. You have to remember, though, that in those days, we actually just knowing where you were in the ocean was a problem. So Bowden's conclusions were that they needed to make continuous measurements at one station for a period of the order of a week. Well, that was quite a challenge. And finally, at the bottom there, it may be possible, with the development of new instruments and methods, to make measurements that are independent of the movement of the ship. So not worrying about where it was absolutely, because you were making radar measurements, and knowing actually where the ship was. So that was the challenge of the day. Now let's see where the focus was. Bowden at that time was a scientist working at the then National Institute of Oceanography in Surrey, located somewhere halfway between London and Southampton, in the depths of the English countryside. You might think that's a pretty strange place to have an Institute of Oceanography. The building is seen on the right-hand side, that rather austere flat-roofed building, which had during World War II been an Admiralty building in which naval radar had been developed. And it was taken over and became the home of the British National Institute of Oceanography in 1954. And it took in biologists who'd been working in the Southern Ocean on the discovery investigations. It had taken in people who'd worked for the Admiralty during the World War II on various problems. Amongst them was the director of the Institute, Sir George Deacon, later to become Sir George Deacon. So that was the focus of UK oceanography from 1954 until 1994. Now I want to introduce you to John Swallow. John Crossley Swallow, born in 1923. Here he is in 1950, then aged around 27. He, as I said, grew up in Yorkshire. He'd been to Cambridge University. He'd worked a little bit for the Admiralty during World War II. And then he'd gone back to Cambridge to do a PhD in geophysics in the Department of Geodesy and Geophysics in Cambridge University. What he'd worked on was the development of seismic techniques to find out what lay below the deep ocean floor. Doing this by setting off explosive charges and listening to the echoes as they came back from the seafloor and from the layers below the seafloor using sonar buoys. And much of that time doing his PhD, he was working on a ship called HMS Challenger, which during the 1950s went around the world. So John Swallow had a lot of experience of seagoing. He knew about building equipment and maintaining it so that it would work at sea. He knew a lot about navigation. The other thing he learned about was the compressibility of both seawater and of the rocks below it, and of bits of instrumentation. And he was spotted by George Deacon, the then director of the institute, and offered a job at this new institute in Surrey. And so he joined it, and he was charged with solving this fundamental problem. How could you measure reliably currents deep in the ocean? Just a reminder of the technologies of the mid-1950s. There was the research ship of Discovery with a steam reciprocating engine and steam-driven winches. Navigation out of sight of land was largely by sextant and star sights. And just coming into being were the very first transistor radios. Most electronics had thermionic valves in it. So John Swallow started to think about this problem of how could you measure currents deep in the ocean. And the first idea he had was to put something on the deep ocean floor, to also put some acoustic beacons on the deep ocean floor. And acoustic beacons had been in existence for some while. Few people know that actually in the middle of the English Channel during the D-Day landings, there were acoustic beacons on the seafloor to guide ships into the right place. So a little bit was known about that kind of thing. Well, this method was tried and it didn't work very well. It wasn't accurate enough, and the currents were not strong enough to make a significant displacement that was easy to measure. John Swallow then thought rather differently about it. And he thought, what if we could make something, an instrument that was slightly less compressible than seawater? If we ballasted it to just sink at the ocean surface, as it sank, it would gain buoyancy, and that at some level, it would become neutrally buoyant and could drift with the currents at that level. And if you put an acoustic beacon in it, you could perhaps track it from a ship. Well, within the space of about 6 months, John Swallow had built a few of these instruments, costing very little. The Institute had very little money in those days, so here he is, a posed photograph with one of those early buoys, and what it looks like is two lengths of scaffolding tubing, and that's exactly what it was. Two lengths of scaffolding tube bound together with end caps to close them, hanging electronics within it, and hanging beneath it a transmitter to make pings, little sounds. And as you can see, both the cat and the two sailors looking on look somewhat bemused by this. Well, within the space of 6 months, John Swallow had made the first of these and taken them to sea, first on the ship called the Sarsia from out of Plymouth. And when that gave some encouraging results, he went out on a cruise on Discovery 2, the ship that I just showed the picture of, into the area of the Iberian Abyssal Plain, west of Portugal. And first problem was to know where you were. And so you put down some buoys with a radar reflector on them, which would move around, but they would give you some idea of where you were, and launch the floats over the side. Here's a picture of a diagram from the paper that was written and published in 1955, so very shortly after the experiment was done. He put several of these into the water. The way they were tracked was that there would be two hydrophones hanging at the forward end and the after end of the ship, and you'd let the ship's orientation change, and so you could see when the two signals from the hydrophones coincided, and that would give you the direction in which the float lay. Each float had to be weighed rather carefully. It weighed about 10 kilograms and had to be ballasted to within about a gram. This was done in a tank in the stairwell of the Institute, and done with a chemical balance, and done very carefully, usually at the weekends when there was nobody around to cause any disturbance. So, remarkably, John Swallow solved this problem very quickly and started to make some measurements of deep currents over the Iberian Abyssal Plain. John Swallow was not alone in thinking about this problem. In Woods Hole, Henry Stommel, similar age to John Swallow, published a letter in Deep Sea Research in 1954. Actually, he'd come up with the same theoretical idea that John had building this this neutrally buoyant instrument, and Stommel was very much a theoretician, and so he put it to the engineers at Woods Hole, including Al Vine, who ultimately designed the Alvin submersible, which became very well known. And Al Vine concluded that it was impossible to do it. They were thinking of a float which was filled with petrol and heated electrically to change its buoyancy. It didn't work, and he decided it couldn't work. And the idea that they had was not just to have a little pinger on board, but to have something that would fire off loud charges that could be tracked over a long distance and navigated that way. So Stommel had come up with the same idea, but thought it was not possible. It's interesting that after John Swallow had died, he was then a fellow of the Royal Society, in the biographical memoir written by Henry Charnock, had this little anecdote. John Swallow and Henry Stommel were very different. Henry was a sort of Ariel to John's Prospero, more ebullient, more outgoing, and more talkative. They became friends and had a tremendous respect for each other. Stommel regarded John as the greatest and most dedicated oceanographer of my time. So Stommel was the ideas man, and John Swallow was the doer and the fixer and the man who made things happen. So Stommel was also at that time working on the theory of ocean currents, and particularly on the theories of why there were strong, compact western boundary currents on the western side of each ocean basin, and how the interior flow worked and how the deep flow worked. And he concluded, working with Ahrens, that beneath the Gulf Stream there ought to be a southward flowing deep countercurrent. And so he worked with John Swallow, and using Swallow's floats to try and prove that it was actually true. They did put some floats down there and explored the southward going flow beneath the Gulf Stream. So this was a partnership that was becoming very fruitful. A theoretician on one side of the Atlantic, a very practical man on the other side of the Atlantic. Move forward then a few years, and there was a considerable body of experience then of using floats, almost entirely by John Swallow. It is surprising that no one else, even though the paper had been published and people had the wiring diagrams of how to make floats, very few other people took on that challenge. There was somebody called Ted Pachapsky at Columbia University who used some Swallow floats some mutually buoyant floats for looking at internal waves. I have found that the Argentine Navy bought some floats. Whether they actually used them or not, I don't know. But it's surprising that this technology didn't spread further. But it was used to actually explore some real fundamentals of the ocean circulation. And the next step was in 1960. And here was again a very good example of the partnership between Swallow and Stommel. The idea was that why didn't they explore the what was thought to be the very sluggish circulation that would be found in the interior of the deep ocean, far away from the western boundary? The idea was that they should mount an experiment somewhere in the middle of a convenient ocean. They chose the Atlantic, and they chose Bermuda as the base, and they would do a year's worth of measurements with some of Swallow's modified floats with a timer on them, because it was expected that it would move very slowly, and you could launch the float, locate it, go back in, come back out in a week's time, and it wouldn't have gone very far, so you could relocate it and go back week after week to find out where the floats were going. The ship that they chose to do it, and this was the benefit of collaboration between the rather poor Institute of Oceanography in the UK and the much wealthier Woods Hole Oceanographic Institution, which had just been loaned this very beautiful ketch called the Aries. It had actually belonged to R.J. Reynolds, the tobacco magnate, who donated it, probably as a tax dodge, to Woods Hole, and they were using it as a research ship. So, with some funding, some American funding, the Aries was used for a whole year, based in Bermuda, and John Swallow, Jim Crease, people like Alan Robinson, then a student at Harvard University, based themselves in Bermuda and started this experiment. The floats worked, but the problem was that they kept disappearing. When they went back a week later, they weren't where they were expected to be. But a few were then found quite a long way from where they expected to be. So the experiment was modified so that the floats could be tracked, not with the timers, but continuously, as they had been doing on the Iberian Abyssal Plain. And what they found was that instead of the currents being a few millimeters per second, they were at a few centimeters per second. This was quite unexpected and quite counter to the theory prevailing at the time. The only paper published on those results at about that time was by Jim Crease in 1962. And what it actually had revealed was that the ocean was full of what we now call mesoscale eddies, much more energetic motions than the background motion that was expected. So the Aries experiment was a success, but in a way that was not expected. This was an idea of measurements really showing that the ocean differed from how theory predicted it ought to be. So it's about this time that I come on the scene. My first cruise was in 1966 aboard the RRS Discovery on Cruise 10. That's a picture of me having just grown my first beard. And my challenge then was to not use nuclear buoyant floats, but moored current meters of various types, which was a new technology that was just being developed to try and measure long time series of ocean currents. We were using nuclear buoyant floats on that Cruise 10 with John Swallow. The tracking technique had changed rather. And here's a picture, actually not taken on that cruise, but a picture showing what a nuclear buoyant float looked like at that time. It wasn't two bits of scaffolding tube, it was a proper aluminium tube closed with end caps and O-rings, the same kind of transducer. John Swallow on the left there had grown a much bigger beard, and on the right you see Gordon Boatman from Woods Hole, and this was actually on the Erica Dam in 1966, making measurements in the Labrador Sea. The technique for tracking it in those days was to tow pairs of hydrophones behind the ship and display the signal coming in from the float on a facsimile recorder, a MuFact, and that's a picture of John Swallow sitting in the plotting office on Discovery at about that time. Actually, he's just echo sounding then, but you could see these beautiful arcs tracing out on the MuFax facsimile recorder, and you could immediately see when first one pair of hydrophone and then the next one came a beam of the float, and you could track them really quite accurately. There were quite a few experiments done using that kind of technique. Um, Let me just go back a little bit. Uh, we were starting to explore various processes in the ocean. Um, One of the big experiments that was done at that time uh, was in the Western Mediterranean, looking at convection in the wintertime in the uh, Gulf of Cadiz. And we used swallows floats there, but we also, American scientists, particularly someone called Art Voorhees from Woods Hole, um, just decided that you could put the floats with angled vanes around them, and since we were looking at vertical convection, if the water was moving up and down, it would make the floats rotate, and if you put a compass inside it, you could measure the rate of rise and fall of the water as it passed the floats. And so that was another rather novel application of neutrally buoyant floats. So that was in 1969 and 1970. Actually, we were starting to enter a very new phase because that was the first cruise on which Discovery had a computer, and the very first cruise on which we had satellite navigation equipment. So we were starting in about 1969, 1970 to enter a new era of technology. There were novel developments going on elsewhere in the United States. In in 19 this was a development by two people, Tom Rossby, who was then at the University of Rhode Island, actually the son of Carl Gustav Rossby, the world-famed meteorologist, and Doug Webb, who was another very innovative engineer. They built a much bigger version of Swallow's float. And this is a picture of it. It's a spun steel sphere about 1 meter in diameter, so it's clearly much bigger, done so that it could carry a lot more batteries, and hanging beneath it, a very different looking sound transducer. It produced sounds at a different frequency range. Swallow's floats worked at about 10 kilohertz. These are at 550. It says kilohertz there, it should be hertz. So a much lower frequency, but with an acoustic range of about 1,000 kilometers. And these would be listened to by listening stations that the US Navy had around the western seaboard of the United States. This was a big innovation. The sound could be heard over that distance because of the so-called SOFAR channel, the sound speed minimum at about 1,000 meters depth, which focused sound and allowed it to travel over huge distances. And so Rossby and Webb actually built a prototype and tracked it for a year, proving that you could start to measure currents over much bigger scales than previously, and releasing you from having a ship to track them the whole time. This was in the lead up to what was one of the most innovative experiments that was done, the mid-ocean dynamics experiment in 1973, going back to the area off Bermuda where the Ares had worked, using CTDs, moored current meters, and SOFAR floats based on the design that Rossby and Webb had used, but with a lower frequency sound of about 260 hertz. The listening stations were run by NASA, and they were there to actually listen for or detect the impact of missiles falling, test missiles falling into the ocean. So that was run over a period of, in the field work with ships over a period of about 3 months. But what were deployed were a large number of low frequency floats deployed in that mode area and then tracked as they moved around. Stommel was involved. You see him having a bit of an argument with Alan Robinson about some theoretical point in the design of the mode experiment. Those SOFAR floats, and there you see them on the left, far bigger than anything that Swallow had. They weighed many, many kilos, and there is a picture of the so-called spaghetti plots of where the floats had gone. What you could see there was that they were being affected by the eddies in the ocean, the eddies that had been hinted at by the Aries measurements. And by then also we had sufficient computer power to enable us to analyze those rather squiggly and random looking tracks and to show that they were indeed tracking eddies, and you could see the way that the eddies were propagating. And here is an analysis that Howard Freeland and I did on those float tracks from the mode experiment at various depths and showing the propagation of eddies through the area. As time went on, those floats were tracked for a long period of time, and many more were deployed in the Western Atlantic. We also had some in the Eastern Atlantic. The Institute in the UK, then by now called the Institute of Oceanographic Science, also wanted to look at the circulation of the Northeast Atlantic. We wanted floats to go deeper, and that couldn't be done using aluminium tubes. So we used glass spheres, and here's one of them being deployed from the Royal Research Ship Charles Darwin. It's cased in a sort of metal frame, which then dropped it. At the bottom, you see the organ pipe resonator at a frequency of 260 hertz. One sphere for buoyancy, two carrying batteries, and the other one for electronics. And they were tracked around in the ocean. We didn't have listening stations that NASA had, so we actually had to put autonomous listening stations on moorings to receive the signals from these floats. And they were analyzed, and over time we built up a picture of the circulation of the Northeast Atlantic. So here we are. Here's a review of the early landmarks, the first direct measurements of deep flows in 1955. 57, the confirmation of the undercurrent under the Gulf Stream. 1960, the first observations of mesoscale variability. Vertical motion of internal waves. 1970 in Medoc, vertical motion of convective regions. Then objective analysis of mesoscale eddies, Gulf Stream dynamics, and finally the tracking of MEDIs in the 1980s. And we could put together a picture of the circulation in the Northeast Atlantic. Henry Stovall, ever the visionary at that time, started to think that this was really entering a new era. And he wrote an article in the Journal of the Oceanography Society about the Slocum mission, a vision that in the future there would be the possibility of having a central place where you could control a whole lot of robotic instruments that would be collecting information from the ocean and using it to actually show the state of the ocean. So this was in 1989. Quite visionary. Certainly, there wasn't the capability of doing it then. So we move on. We have now we now have satellites. We have satellites that have enabled us to measure things globally. We could look at the shape of the ocean surface and how that responded both to the heating of the ocean, but also to ocean currents deep down. We had reliable and sophisticated instruments to measure temperature and salinity in the deep ocean. And we could contemplate moving from observations on a basin scale to observations on a global scale, and to look at the role that the oceans played in the climate. So this was the so-called WOCE experiment, World Ocean Circuit experiment, which was planned during the 1980s, observations during the 1990s, and then followed by analysis. And the guts of it were two components: the grid of CTD stations and chemical tracer measurements along the lines you see in that grid, plus satellite altimetry. But just as we had originally with the dynamic method, there was a need to have global subsurface observations of velocity. And how could that be done? Well, the breakthrough then was made by Russ Davis at Scripps Institution of Oceanography and Doug Webb, who we've already heard about, who designed the autonomous Lagrangian circulation explorer, effectively a swallow float that would drift around below the surface of the ocean, but it could change its buoyancy. It could change its buoyancy by pumping oil from an internal reservoir into an external bladder. Mass of the float would stay the same, the volume would increase, so the density would decrease. It would come to the surface. It would then transmit its position to an overflying satellite, would suck the oil back into the reservoir, sink back down to the same level, and drift on for a while longer. And these were designed specifically to solve this problem of, within WOCE, making measurements of the deep circulation. They were deployed along the WOCE lines. You can see the dots in the top there of where they were deployed and where they finished up. And on the right, a schematic of the float profiling cycle. Let me just look at time. And we did indeed manage to make those floats work and could map out there's a map of the circulation of the Pacific Ocean, the deep ocean circulation. But at that time, the idea came, well, if you could have this thing profiling up and down, and you could put a CTD on it, could we measure the temperature and salinity as the float came to the surface? And that was indeed done. And towards the end of the WOCE experiment, there were profiling P-ALICE floats. We explored the North Atlantic with them. And so here are the catalysts for the Argo program. The success of the ALICE and PALICE floats in WOS, the advent of CLIVAR, which enabled us to continue WOS-like measurements beyond the 1990s, and two proposals that were put forward. One called Gossamer, Global Ocean Salinity Monitoring, put forward by Ray Schmidt, and the Argo Array for Real-Time Geostrophic Oceanography, put forward by Breck Owens and Dean Remick from the USA. And the catalyst really was the OceanObs conference in 1999, run by Neville Smith and Chet Kablinski, where those two proposals were put forward and endorsed as a means of starting to monitor the global ocean. This was followed up by a huge amount of hard work and lobbying of governments and research funding agencies by two Americans, Jim Baker and Stan Wilson. And how it came about eventually was that there would be floats commercially produced, derived from the WOS PALICE, some made by Webb Research Corporation, a company run by Doug Webb in the USA, some generated in France by a company called Martech, and a large number made by Scripps Institution, the solo floats from the USA. There would be contributions from countries, and there would be an agreed basic cycle of profiling every 10 days, cruising at a depth of 1,000 meters, but also going down to 2,000 meters before they profile to the surface. So you could get profiles of temperature and salinity over the top 2,000 meters of the ocean. Communication initially was by the system Argos. Each float would cost about £15,000, and you could double that for the add-on cost of deployment. And the target array was a 3x3 approximate array of 3,000 floats, with a float lifetime of between 3 to 4 years, which meant we needed to deploy about 800 floats a year. The total cost of that would be about $24 million per year. Countries signed up to it, and so here's the profiling cycle. There would be national contributions, large and small. The idea was that everybody would share their data openly, and that was one of the criteria for being part of the Argo project. There would be timely, real-time exchange of data, but it also would be quality controlled in detail and circulated in delayed mode. Through the IOC, the International Oceanographic Commission, there would be negotiated access to EEZs, and it would be done in support both of research and operational users, and would be a pilot program of the Global Ocean Observing System and the Global Climate Observing System. Argo changed its name from the Array for Real-Time Geostrophic Oceanography to just Argo, because it was, as in Greek mythology, partnered with the Jason satellite altimetry. By mid-2020s, Argo had grown to deliver over 2 million temperature and salinity profiles, and had a large and growing user community with, by then, over 5,000 papers citing Argo since 1998. It has had an enormous impact on our knowledge of the oceans. I started with that picture that anybody could guess or get of where temperature, what the temperature and salinity was in the most remote parts of the ocean, but also you could measure ocean heat content really quite reliably. And here is Cheng et al. That's a 2021 estimate, and you can see first of all the error bars are rather large. I've put them on, I've just highlighted them then, and how they become much smaller once Argo comes in around the year 2000. So that's where we are today. We actually have an array of 4,000 floats, some of them operating in ice-covered areas, some in marginal seas. Here's an overview of all the steps that we've taken, indeed, from 1950 up to 2000, the 50-year development program from swallow floats to Argo. And here is the array as it is today with about 4,000 operational floats. Countries involved there, 23 countries, with the USA providing half of those floats. We hope that that will continue. We live in interesting times. They need to be maintained, and some concern is whether one worries if the USA part of that array were not to be supported by the federal government in the USA. But that's probably an issue that's far beyond the scope of this talk. So I'm going to close with a little animation produced by Howard Freeland, showing the growth of the Argo array from its start in 2000 until the full array was built. Timeline you can see at the left, 2007. By then, we'd just about reached the full 3,000 float array, and here it is continuing. And on the right, the people who really played a huge role in making this happen. Henry Stommel, John Swallow, Russ Davis, Doug Webb, and Dean Remick, who has been a force behind Argo from beginning to end. And Argo, in some ways, has partly fulfilled Stommel's Slocum vision. And John Swallow, who didn't live to see Argo come into fruition, would, I think, be pleasantly surprised. Thank you.
Thank you, John. That was an excellent summary of the history of making hydrographic measurements. If people have got any questions, could they put their hands up or could they put something in the chat, please? Well, one question I had, what was the Slocum business? What was that?
Well, this was his vision of actually gliders traversing the ocean and collecting temperature and salinity data.
So Slocum was a person.
Sorry?
Slocum was a person or a...
Yeah, Slocum was Joshua Slocum, who was the first person to circumnavigate the globe single-handedly.
Oh, okay.
In the late 1900s. Sorry, I meant to mention that. Yep.
Okay.
Read his book, The Voyage of the Spray.
Right. Okay. Okay. Dave, do you want to ask your question?
Yes, please, Phil. Can you hear me?
Yep.
Yep.
Oh, excellent. Right. I was struggling to find how to put my hand up. So my question, John, is you've given us a very good account of the development of tracking ocean currents below the surface over the last 50 years.
Yep.
What do you see as the main things that might happen in the next 50 years?
Ooh, no, you're asking me to have a crystal ball. The most optimistic, well, I think two things will happen. Two things I hope will happen. I hope Argo or its successors will continue because clearly monitoring the state of the ocean and monitoring the currents is of huge importance to our understanding of climate and its effect on the planet. One of the limitations I think that we have now is that in some senses our ability to measure salinity in the deep ocean has not really changed very much from the era of the Wace experiment, um, and yet our understanding of salinity, with Trevor McDougall's bringing about the concept of absolute salinity, has gone much further. And are there? One wonders if there are some novel ways of measuring salinity that don't rely on our measurement of electrical conductivity. In some ways, that's um, a rather convoluted way of getting at salinity. So I would hope that at some stage we might develop new ways of measuring salinity that have sensors that are stable. One of the big challenges of Argo is maintain the calibration of the instruments, because some of them last in the ocean for as long as 10 years, and to put an instrument in the ocean whose calibration doesn't change for 10 years is a huge challenge. So those are the two of the things. I'd like Argo to continue, but I would also like to see better salinity sensors.
Yeah, just anybody who's not seen it, Paul Abrahamson has put in the chat about a link for the Slocum sailing around the world.
Yep, good.
That's good.
Sam's got his hand up.
Sam, yeah.
Thanks, John. You mentioned quickly at the end there open data. Was there a creation of a legal data instrument for this project, or how does that work? I understand that if you join the project, you sign in, but how is that enforced or maintained?
It's signed up to basically through the IOC, through the Intergovernmental Oceanographic Commission, which is part of UNESCO, part of the United Nations. So just as with any meteorological exchange agreements, that's the same sort of process. And that works well as long as people abide by it and abide by international treaties and agreements. All of a sudden, we call some of those things into question, and that is a worry. But there have been some glitches along the way, but by and large, we've always overcome them, and the sharing data hasn't been a problem.
Thanks.
Yeah. Well, let's hope so. And the same applies to many other data streams, isn't it? So,
indeed.
Anyway, Gwyn has got his hand up as well.
Thank you, John, for your talk. Around 1978, if I recall, Wormley colleagues Dennis Gaunt, Mac Harris, and others worked on a Nautilus float, a rather cumbersome idea, but it did have a buoyancy engine, and it certainly predated the US efforts, but it didn't really make the transition into use. From your perspective as perhaps the customer for that, John, why not? And what could Wormley have done differently in that era?
Um, I think that you've touched on a rather fundamental issue of the development of technologies. There have been, and I think if you go back through the history of particularly British oceanography, there have been many technology developments that have not initially been quite as successful as they were expected to be. And funding agencies like success, and they like, by and large, they like quick success. And the challenge, I think, is to maintain fund, to have a clear vision of what it is you want the instrument to do and to achieve, but also B, to have a commitment from the funding agency to support you through thick and thin, and to really not pull the plug until it really doesn't, either doesn't do what it said on the tin, or it really doesn't work. The danger is that money just runs out too quickly, and funding agencies pull the plug, and then you move on to something else. I think the other issue is the Argo float, the Palace float, was designed to be built in large numbers for relatively low cost. And that then makes it attractive to commercial operators to take on and build. Building a thing that just is only going to be used in ones and twos is not usually cost effective. You probably have more experience of this than I do, Gwyn. So I don't know whether you agree with my assessment.
I'm sure that those points will come up in my auto talk.
Very good. We'll wait for that.
Well,
They are generic, but again, I think it shows, the inventiveness of the technical staff at Wormley, which
Yeah.
I'd like to put on record in this recording.
Yeah, I think that's right. And the other point I made, and I think is interesting, is that this technique that John Swallow developed, it really didn't spread until it became effectively almost commercially viable. Nobody else was willing to take on and adopt the black magic and the commitment that John Swallow had to make to weigh each individual float and to treat each one as, he put in hundreds of these floats, but each one was his thing, and he applied huge amount of effort and detail to make sure it was right. And very few people are willing or able to do such a thing.
Yeah. Pamela? Okay, Gwyn alluded there to the talk he's going to give in the series, which has changed title. Anyway, it's now called Snippets of Auto Subhistory, a Tasting Menu. So if nobody has any further questions for John, we'll just like to thank him. And I'm going to stop recording now. Is that okay, John?
Fine. Thanks very much, Phil.